For decades, scientists told us nothing escapes black holes. But what if I told you they're not just swallowing everything? They're actually leaking energy and slowly evaporating away. Okay, let's break this down because this is one of the most mind-blowing concepts in all of physics. First, the traditional view of black holes. They're cosmic vacuum cleaners with gravity so strong that not even light can escape once it crosses the event horizon. That's the point of no return, right? Well, that's what Einstein's general relativity told us, but then in the 1970s, Stephen Hawking came along and dropped a bombshell that merged quantum mechanics with gravity, and everything changed. The key to understanding Hawking radiation lies in something called quantum fluctuations. See, even in complete vacuum, space isn't truly empty. It's a bubbling, seething sea of virtual particles that pop in and out of existence constantly. These are particle-antiparticle pairs that form spontaneously, borrow energy from the universe for a split second, and then annihilate each other to pay back the energy loan. Normally, this happens so fast and so close together that we don't notice it, but when this happens right at the edge of a black hole's event horizon, something extraordinary occurs. Imagine one of these virtual particle pairs appears just at the boundary. One particle might fall into the black hole while its partner escapes. The particle that falls in has negative energy relative to the outside universe. Since energy must be conserved, the black hole loses a tiny bit of mass energy equivalent to the positive energy particle that escaped. From our perspective outside the black hole, it looks like radiation is coming from the black hole itself. This is Hawking radiation, and here's where it gets really wild. This radiation isn't thermal like starlight. It has a temperature. Hawking calculated that the temperature of this radiation is inversely proportional to the black hole's mass. So smaller black holes are hotter and evaporate faster. A black hole with the mass of our sun would have a temperature of about 60 billionths of a degree above absolute zero, meaning it would take longer than the current age of the universe to evaporate significantly. But a tiny black hole, the size of a mountain, would be incredibly hot and evaporate in a flash. As the black hole loses mass through this radiation, it gets hotter, which makes it radiate even faster. This creates a runaway process where the evaporation accelerates until, in the final moments, the black hole would explode with the energy of millions of hydrogen bombs. Now, you might be thinking, has anyone actually observed this? The honest answer is not directly yet. The radiation from stellar mass black holes is too weak to detect with current technology. But there's strong indirect evidence through thought experiments and mathematical consistency. The implications are enormous. If black holes can evaporate, they're not the eternal prisons we thought. Information that falls into a black hole might not be lost forever. It could be encoded in the radiation. This touches on the famous black hole information paradox that's still being debated today. What's truly revolutionary is that Hawking radiation represents the first successful marriage of quantum mechanics and general relativity. It shows that these two pillars of modern physics, which have been notoriously difficult to reconcile, can actually work together to predict unexpected phenomena. So next time you look up at the night sky, remember that those mysterious black holes aren't just cosmic trash compactors. They're radiating, they're changing, and they're teaching us profound lessons about the fundamental nature of reality itself. What's the most surprising thing you learned about black holes today? Drop your thoughts in the comments and follow for more mind-bending science.